Turner, and my project is axial transport of electrons in a pinning trap. So basically that means moving electrons from E2 to E3. What's the best way to do that? And this will be part of a general scheme of pieces that they'll do on graduates. So first off, I need to introduce what plasma physics is. So for the purpose of this talk, a plasma is just a cloud of ionized gas. That's an insult to Joel and all plasma physics, but that's effectively good enough for this talk. And so we work with even more specialized type of plasma called non-neutral plasma. So this basically means you have one type of plasma, one type of charge inside your plasma. And so what you do this for is it has better trapping properties and it can go to low temperatures. That's the main thing, is it doesn't recombine at low temperatures. So you can have a low temperature plasma of one type and trap for a long time. And the image there is a MCP density of charges, so that's the current or data analysis that we use for a lot of things. And so the main tool we use inside our experiment is called a pinning trap. So theoretically, non-neutral plasmas can be trapped indefinitely for perfect traps, ideal situations. So what you have here is you have a magnetic field B represented by the orange lines. So in this model, we're assuming they're just perfectly all uniform and straight going that way. And what this does is it traps it radially on a fixed radius, and that works to keep it from expanding to the walls. Axial trapping, which is the part that I'm most concerned about for this project, is done by applying a voltage plus V to one of the electrodes. So for this instance, it's the trap of E2, so the cloud of the plasma is trapped in E2 around the center. So, my project. Optimization of axial transports of electrons in the pinning trap. So by optimize, I mean this very strict definitions. I need to minimize heating, I need to minimize expansion, I need to minimize loss in the plasma. So why do these things matter in this experiment? So this pinning trap has a common geometry between the one at CERN with the alpha experiments, the anti-hydrogen laser physics apparatus, a similar trap geometry to ours. So techniques used in this experiment can be applied to that experiment. And one of the reasons why you want to have minimized loss, minimized expansion, and minimized heating is that trapping anti-hydrogen is very hard to do. You want to minimize any kind of heating, any kind of loss of any particles along the way. And it's also good to maintain stability because you have certain radiuses. It's nice to always know what you have in different steps. And it's also interesting because last summer I worked there and I worked on a problem which involved transporting electrons, and I just want to understand why that happens. I want to get a better solution of why it happened the way it did. It's my method. So basically, you have an electron in a potential. And you apply a potential and it's trapped there. So that's your first step. And you keep it in that electrode for some amount of time, wait until you go to the next step, where you apply a second potential on electrode 3 probably, right? Electrode 3. So it's trapped in electrodes 2 and 3, and what you change in this process is how fast you ramp electrode 3. So you can determine that ramping rates and how long it stays in this well. And those are parameters that will help you, and also the size of the potential. And those are parameters you can optimize to try to figure out the best way to do this transport. So the final step is lowering the potential in E2. And so you have now trapped in E3. And again, you can change how fast you unload E2 and then lower the voltage. So that's the general layout of what my goal is for the project. And this is just a simplified model. There are like 20 electrodes in the actual experiment. This is one model because you don't really need that many electrodes to figure out this process. So theory. So I started the summer trying to do experimental stuff, but the experiment had technical difficulties. So I tried to become a theorist for the summer. And so I started off with the basic model of a single particle in a trap. This is a well-studied problem, and it's basically you solve you use the lens force to figure out the motions based on the electric field and the magnetic fields. And so you have smaller circles called cyclotron, for cyclotron motions. You have the larger circles, which is magnetron, and you have the axial frequencies, oscillations. So for me, I mostly care about the axial motion. There are some details in the code where you need to like sync the cyclotron period with the code steps to make it work properly. But for me, I mostly care about axial, and this code is me. It's a two-dimensional RZ kind of problem. So after I figured out this single particle trap, I decided to move up because my thing is not single particle; it's many particles. So I tried a plasma trap. This is a very hard problem. There's no analytical solution. You can't really do it by hand. You can't like, write equations. It's a messy thing. This is currently the work of a grad student in our theory side of our group. And so it's not something I can tackle at this moment, and he's working on it. But it's an interesting problem, and it's complex equations, but I talked to the theory person in our group, Jonathan Wordley, and he said I should try using simulations. And so the simulation he suggested was warp. So warp was a simulation made in LBL in the early 90s, late 90s, to figure out accelerator physics stuff, but then it became applicable to plasma physics. So it's basically a mixture of Python and Fortran. So I decided to learn Python and Fortran this summer, and then learn warp. And so that was the middle of my summer was trying to figure out how to do all this stuff. And so basically how warp works is you have initial conditions. So you have placement of particles and the velocities. So you have that initial gather forces and all that stuff, the first step. That's equals 0. Then you push the particles using all the forces. And so with all the different forces, you say where they go in a certain time step. That's a very small time step. It's like 10 to the minus 12 seconds in the time step. And so they see, okay, after you push them, where are they now? And so you do that again, and you figure out, it's okay, so now we have all these new particles, all these same particles, but new positions and new velocities. So what's the new charge density and the new currents? Because that'll change the fields, because they're self fields. So it's a very complex problem. And so then you move on, and you solve the fields, and you keep doing this over and over again. And this is like over seconds, so it's like 10 to the 12 like steps. And so I haven't really done the full simulation yet because I'm getting access to the server next month. But still, I did a small segment of this to show proof of concept of what can be done for this. So the first thing I tried to do was, okay, so I want to apply potential to electrode 2 and see what happens. So what it does is you have the little cloud in the middle. Those are electrons. It's about 1,000 electrons, which is smaller than the million we usually have, but it's computationally again too heavy for my computer to handle that. So that's what I got. So on the left side, you have contours showing where it basically is, and you see they're at the minimum. You can confirm with the minimum by the energy minimum by looking at the plot on the right. And it's a minimum because from basic physics like 7D or like 8D, you know that the energy associated with the potential is the charge times the potential. So Q is negative times the positive potential means that along the middle they'll be kind of trapped. And that's basically from the electric moments, the electric field. And it's a magnetic field you can find in its rings. So they're trapped axially by this electric field and radially by magnetic fields. And so then I move on to these seconds. And you see that when you apply a fixed potential between E2 and E3, you get an expanded region. And again, they're trapped in the middle. So in the middle of E2 and E3, they're there. And it works, and it's very nice. So the last step is then you go to E3, and they're trapped at this position. So this wasn't the full simulation. This was basically showing each step and how the simulation works. So after this process, I decided to actually do the full time iteration and time steps. And so I looked at heating. And so basically, what this does is I start off particles at the green pipe, the green spike. So that's a Gaussian distribution of velocities in the axial direction. So they start there at t equals 0. So I have two methods of getting them from there to the end. I gotta change the potential instantaneously, and that's in gray, or I can change them with a slow linear ramping time. And I chose one of the ones I wrote in the one, which is 0.1 microseconds. So you can see that the gray is not optimal at all. But you can see that the axial velocity is a huge spread, and they're high velocities, and it's very bad because the velocity associated with energy is associated with temperature. And so that's very bad, and it's a proof of concept that we know this is known fact that you should not ramp the electric fast because it's easy constant. And so again, the linear ramping shows a more efficient model. So it's not perfect because there's still some mismatch in the ramping time, but it's effective. And over the next few weeks, I'll be trying to figure out the best ramping time because I don't want to be too long, because you don't want to wait forever for it to ramp. And it doesn't want to be too slow to cause the instantaneous spikes. So, there are plenty I can do in the future to improve my code and my simulations. I can run the complete code time and the correct number of particles and size parameters and actually make a physical problem, which is I'll do that once I'm able to use the server, because my computer can't handle this. I can test or confirm that this is working by creating a different model in MATLAB, which kind of confirm that they correlate, because warp isn't perfect because it doesn't really model interactions very well or at all. As seen here, like it doesn't really model collisions for electrons, which is kind of an important thing, but it's way too computationally heavy. So that's also the project of one of the members of our group, our theory group, who's working on that at the moment. So that's still not something for them. So eventually, I'll do the experiment part of this. So this is my main focus at the beginning. I was going to do experimental, but it's currently getting pumped down at the moment, and it's almost operational. So once it's ready, I have certain tools and diagnostics I can use. I can measure the expansion of the plasma through an image, the image you see earlier. That's the MCP. I can measure the loss by measuring how much charge there is through the Faraday cup. Or I can measure temperature by slowly raising the well and observing what comes out. Because you know at a certain potential, something will come out, so then you keep trapped. So you keep going, raising it until it's nothing's left. You just figure out when they come out. So conclusions. Heating is the most interesting parameter to look at. So that's what I'm going to continue looking at. The reason for that is, since in my code there's angular symmetry in the problem, there's conservation of the angular momentum, so the radius shouldn't expand from my code. So there's really no point in looking at that in the code, because I can't really do that. Simulations have shown that loss is negligible, so that's also something that's, and again, if I had better code, that would work. But again, so those PDs make them looking at the future. So acknowledgments. I want to thank Professor Bill Fajans for being my mentor, Professor Jonathan Borley for advising me on how to use work, the grad students in the lab, Alex, Marcelo, and Albert, the undergrads in the lab, Nathan Shee, Leo Carroll, and Rose Hills and Sir.